we identify the problem of divergence for our refinement model M2. And the way we fix it is by introducing the two variables or flags, ML_pass and also IL_pass, and how they should be manipulated. We talk about them in detail in the previous part. And in this part over here, given these two variables that have already been incorporated into the working for the system, we would like to see how we can formally argue and establish that our M2 right now is actually divergence free, which does not have any life lock. That's something we'd like to do. And based on our learning from proving the previous refinement model M1 is actually divergence free, what do? We needed to come up with the variance expression, and then we try to prove the two obligation. Number one, the variant expression should be non-negative, and number two, the variant expression should be strictly decreasing after every occurrence of the new events. These are the two proof of obligation. I'm not going to do both of them, but I'm just going to do one of them just to brush up your memory. But you should really do as an exercise to really make sure you prove that our refinement model M2 as of now should really is formally divergence free. Let's recall what a variant is, and you should always think about the contrast between variance and invariance. Variance is really something that changes all the time, and invariant is something that should be held true always, otherwise you get a violation. Variance is an integer expression, whereas invariance should be a Boolean condition. And again, what's a variant expression? It should be an integer that characterizes the follows. You should characterize the interleaving of the new events, meaning that if the new events can interleave with each other, the interleaving must be bounded. Otherwise, if the interleaving is unbounded, you definitely get the divergence problem, the life lock. And the variance expression being an integer will make sure since the starting of the new events interleaving, the interleaving will at some point reach the value 0 for the variant expression, in which case the interleaving of the new events should really stop, and then some old events must occur in order to really increase the value of the variance again, so that you can be sure the new events cannot just interleave indefinitely. Right? That's kind of the insight we have been talking about since the last refinements. What can the variant expression refer to? It can refer to constants, or it can refer to concrete variables. And let's see, for our model M2, what can be the variant expression? Let's propose this one here. It's going to be ML_pass plus IL_pass. And remember, each one of them is simply just an integer. More specifically, each one of them can just be either 0 or 1. Of course, if you try to do the addition of them, it's going to be an integer as well. And the range of the addition can be somewhere between 0 and 4. Of course, 0 and 2, beg your pardon. So ML_pass can either be 0 or 1, and IL_pass can also be 0 or 1. So of course, the range of the addition should be between 0 and 2. Let's now try to see how the trend of the interleaving of the new events is going to proceed, and also how the corresponding change on the variant value should also proceed as well. That's something I'd like to show to you. Okay, let's now switch. This table over here is simply just what we did for the tracing over here. I have just copied that into this page over here, right? It's just the same. Now what I want to do is plot some graph over here, right? Remember this graph over here when we first introduced the idea about variance. The vertical axis is about the variant value, and in this case, it's going to be ranging from 0 to 2, as I explained before. And the horizontal axis over here is about the occurrences of the new events, but I'm going to show you some old events as well, not just the new events. To do the sum, for example, 1 plus 1 is going to be 2, right? That's how we started with. So we started with just over here, right? The variant expression is ML_pass plus IL_pass. So 1 plus 1, let me just put the sum over here. So 2 and 1 and 2 and 2 and 2 and 2 and 1 and 2 and 2 and 2 and 2. If you have any doubts about any particular values in this entry over here, you can definitely refer to the tracing that I covered in the earlier part, right? For that one, I'm going to assume you're okay. So these are the variance value over here, right? These are the variance. ML_pass plus IL_pass. We started with 2, which correspond to the post states of the inits events. And let's see what's going to happen afterwards. it will drop to 1 after the occurrence of MLTL green because we set ML pass to be 0. And what's going to happen is it's going to drop to 1 over here, and I will annotate about which events happen after the graph has been plotted. Okay, and then you can see after that we're going to get a series of odd events. It's really important to see that these events are simply the odd events over here. Let me use maybe pink. Okay, so these are the odd events. The odd events. Okay, and it's going to bring the variance value back up to 2 for a while. So what's going to happen is it's going to go back up to 2 over here, and then how many events do we have? We got ML1, ML2, and also ILN, ILN. So we got 4 events. So 1, 2, 3, and 4. All of them is actually going to remain the value to be 2. After that, we got another new events occurring over here. You can think about this part over here is a new events, and this one here is a new event, right? This will be ILTL green. That one there is going to bring the variance value back down to 1 over here, right? So we are still maintaining the principle. Whenever you got any new event happening, it should really drop the variance value like this. And whenever you got any old events, you should really either increase it or maintain the same. At least it cannot decrease it. After this, we got just another series of odd events over here, right? That's, again, odd events. And that one there is going to bring us back up over here. And how many occurrences do we have? We got 1, 2, 3, 4. Just similar as before. Let me just be a little bit more precise. 1, 2, 3, and 4. Okay. That's about the pattern for the variance value over here. Let me do a final annotation just to confirm our principle, and then I'll talk about how we can discharge the proof obligation. We want to do things more formally after the intuition. This part over here about the value decreasing over here, this part, these 2 occurrences are exactly the occurrences of the new events. Occurrences of new events. On the other hand, you can see other part of the graph is actually due to the occurrences of the old events. You can see here the first occurrence of the old events is actually ML out 1 over here, which simply set the ML pass from 0 to 1. That's why you see the uptrend. But for all the others, it's going to remain just flat over here to be 1. So that's why it's simply flat. So if you really want to see exactly what's going on, I can be more precise. This will be ML out 1. And all the other 3, 1, 2, 3 are these 3 events over here. And similarly, after we have decreased the value of the variance by the ILTL green, we got ILL1. So that's the first one which will change the value from 0 to 1 over here. That's why you can see the value of the variance will increase again. And then it will be maintained as 2 by other 3 occurrences of the old events. So this one over here is ILL1 over here. Okay, just gonna be careful. So this one here will be IL out 1. Recap before we move on. Based on the tracing of this particular trace without any divergence, we can conclude that whenever we got any occurrences of the new events, it's going to decrease the value of the variant expression, which will be the addition of ML pass and also IL pass, which is summarized in this additional column over here. And every time there is any occurrence of the old events, it will either increase the value for the variance or simply maintain flat over here. As long as it does not decrease the value for the variance, it will be okay. All right, so you really want to study this with the assumption that you know how to trace the variant value, well, especially ML pass and IL pass. And the next part will be, we want to formulate the 2 proof obligations related to the variance. Let's go back to the slide to have some brush up. Okay. And to really formulate the proof obligation related to variant, there are two kinds we need. This is only the one kind about the var, which is about the value for the variant should be strictly decreasing. That's something I will go over with you quickly. The other one, which will be left as exercise for you, will be about net proof obligation, meaning that the variant expression should always be larger than or equal to 0, i.e. it should be a natural number. And the exercise over here indicates what you should really try to formulate and prove the remaining parts for the variance proof obligation. Let's not go over this one specifically quickly, just make sure you're okay. Let me switch over here. And according to the var proof obligation, the pre-state value for the variance should be strictly larger than the post-state value for the variance. Let me write it down over here. So this is really the pre-state value, pre-state evaluation of the variance. Of course, it depends on the value for ML pass and IL pass. On the other hand, to the left-hand side of the less than, that should be the post-state value. Post-state evaluation of the variance over here. And what we want to do is we want to do this for every new events. The var should be applicable to every new events because only new events may result in divergence. Applicable to new events only. You don't have to formulate this proof obligation for any old events. And let's say the new events we are talking about is ML green. That's one of them. The other one is IL green. That will be left as an exercise for you. And what will be this will be the sequence for the proof obligation, quite giant hypothesis set as always. Let's take a look. According to the definition, we need the constant and also the axiom, right? We need the axiom. So these are the axiom about the D and also the color. And we also need the abstract variance. The abstract variance, abstract invariant, beg your pardon, abstract invariance. Abstract invariance will be the N. This is from model M0. And also from model M1. A, B, and C. And also the extra invariance over here. Right, there's something I can just do a very quick. So this part over here is really the abstract invariant from M0. And this part over here is really the abstract invariant from M1. And also the concrete invariance from M2. What about concrete invariance? The concrete invariance will be this part over here. Concrete invariance 1, 2, 3, 4, and also 5. So these are the 5 concrete invariants that we need. Okay. And also these are the additional ones. So these additional invariant can refer to when we spoke about the fixing of the divergence problem. Let me just show to you very quickly. Right? Just don't be too surprised. If you go back to the earlier part we discussed, you can see these are the extra invariants related to the ML pass and IL pass that we had to introduce to fix the divergence problem. So that's why we got these invariants as well. So in total, finally, we got 9 invariants. Remember, we initially introduced invariant condition number 5, and then we got another 4 due to the divergence solution. Just don't get lost. Okay, let me go back here. These part over here are also the concrete invariants in M2. Okay, let me just highlight them over here. Okay, good. And specifically, these 2 invariants are important for some proofs that you're supposed to do. And you just want to make sure you understand them or reach out to me if you got any question. So for this part over here, these are the concrete invariants for M2. And we also need the abstract guard, beg your pardon, concrete guard for the events. And the concrete guard will be this part over here. 1, 2, 3, and also 4 over here. So 1, 2, 3, and also 4. So these are the concrete guards of MLTL green. So these are the concrete guards. Concrete guards of ML TL green. And the final part over here is about the pre-state evaluation should be strictly larger than the post-state evaluation. So let's talk about that part over there. And how do we work out this goal over here? Let me put a star over here. You should really think about, we want to say the post-state value, ML pass prime plus IL pass prime should be strictly less than ML pass plus IL pass. Think about this part over here is the pre-state value I talked about, and this part over here to the left hand side of the less than is the post-state evaluation. What should we replace the prime over here by? It depends on the before-after predicate for the MLTL green. In this case, let's take a look. We don't need to write out the complete before-after predicate. Let me just write down what's really needed. So the before-after predicate, you can see ML pass prime should be 0. ML pass prime equal to 0. What about IL pass prime that we have over here? Since IL pass is not really mentioned in this action over here, that means it remain the same. And IL pass prime is equal to IL pass in the pre-state, and etc. for other variables, which I'm going to omit just for now. Let's now do the substitution. ML pass prime will be equal to 0. So this part over here is simply just 0. IL pass prime will just be equal to IL pass. So this part over here is simply replaced by IL pass. So this is exactly what you will see over here. I'm just trying to show you the derivation process quickly. Right, and the proof is really up to you. It's quite trivial to actually prove it, but I will still want you to do it. Just make sure you will be able to do it independently, maybe in the assessment. Alrighty, so now we are done with the discussion on the divergence, and the next topic will be relative daylight freedom.